Welcome to everybody. Probability and stochastic processes. In today's session, we will see common random variable distributions. I am Dr. V. Ayyambillai, Professor EC, GRIT, Hyderabad, India. Let's have some introduction. There are some specific distributions that are frequently observed to be associated with a lot of real-world phenomena. Hence, they need special names and analysis so that systems can be designed and analyzed. Binomial and Poisson are commonly observed discrete distributions. Gaussian, exponential, uniform, and Rayleigh are commonly observed continuous distributions. First, let's see binomial distribution. We have seen Bernoulli trials. Considering capital N trials and K successes, the probability of K successes have been seen to be NCK p to the power k 1 minus p capital N minus k, where p is the probability of success and 1 minus p is the probability of failure at a single trial. Distribution function is a concept of probability of less than or equal to. Hence, here we talk as probability of less than or equal to k successes, for example. Binomial distribution function is defined as follows. Capital Fx of x, which is probability of capital X being less than or equal to small x, is equal to sigma k is equal to 0 to capital N, NCK, p to the power k 1 minus p the whole power capital N minus k u of x minus k. The upper limit is capital N because this is general expression permitting up to capital N successes or capital N failures. U function, that is unit step function, is there to convey that probability is there only for greater than or equal to 0 values of x, because number of successes or failures are greater than or equal to 0. The corresponding density function is differentiation of distribution function. Small fx of x is equal to sigma k is equal to 0 to capital N, NCK, p to the power k 1 minus p capital N minus k delta of x minus k. Binomial distribution with capital N is equal to 6 and p is equal to 0.25 has been shown in the figure on the next slide. So you see that the distribution function is a staircase type of waveform and the density function is of impulse functions. Next, let's see Poisson distribution. Poisson random variable applies to a wide variety of counting type problems. Counting type applications. It describes the number of defective units in a sample taken from a production line, the number of telephone calls made during a period of time, the number of electrons emitted from a small section of a cathode in a small interval, etc. It can have only non-negative integers. Poisson distribution is associated with a concept of parameter defined as B is equal to lambda capital T, where lambda is an average rate and capital T is time of interval. This distribution is similar to binomial distribution. In fact, as capital N tends to infinity and small p tends to 0 in the binomial distribution, such that capital N small p is equal to B, we get Poisson distribution. The density and distribution functions are defined as follows. The distribution function of Poisson random variable is as follows. Fx of x is equal to sigma k is equal to 0 to infinity e power minus b, b to the power k divided by k factorial u of x minus k. The density function of Poisson random variable is as follows. Fx of x is equal to sigma k is equal to 0 to infinity e power minus b, b to the power k divided by k factorial delta of x minus k. Next, let's see Gaussian distribution. Gaussian distribution is the most important of all distributions. Gaussian distribution is the most important of all distributions. The reason for this lies in central limit theorem. Many random variables in real life can be described as summation of a large number of random variables. Central limit theorem, which we will see later, states that the probability distribution of a summation of a large number of arbitrarily distributed random variable approaches Gaussian or normal distribution. The PDF of Gaussian distribution is as follows. Fx of x is equal to 1 divided by within root 2 pi sigma x squared exponential of minus of x minus ax whole squared divided by 2 sigma x squared, where sigma x is greater than 0 and minus infinity less than ax less than infinity are real constants. Sigma x is called standard deviation. Sigma x squared is called variance and ax is called mean of random variable. These concepts we will study later. The CDF of Gaussian distribution is as follows. Capital Fx of x is equal to 1 divided by within root 2 pi sigma x squared integral of minus infinity to small x exponential of minus of u minus ax the whole square divided by 2 sigma x squared du. The Gaussian density function follows a bell-shaped curve and the corresponding distribution function has been shown. Both the density function and the distribution functions have been shown on the slide. Next, let's see uniform distribution. Uniform probability distribution arises when for every equal range within the whole range of random variable, the probability is the same. This distribution arises in many practical cases. For example, the quantization error in signal processing closely approximates uniform distribution. Since PDF is per unit probability and the probability is the same for every equal range within the whole range, we can write PDF as a ratio of total probability to total range. The uniform PDF is defined as follows: fx of small fx of x is equal to small fx of x is equal to 1 divided by b minus a for the range between a and b, that is a less than or equal to x, less than or equal to b, and 0 elsewhere. The uniform CDF, which can be obtained by integrating PDF, is defined as follows: capital Fx of x is equal to 0 for x less than a, x minus a by b minus a for a less than or equal to x, less than or equal to b, and 1 for x greater than or equal to b. The curves of CDF and PDF of uniform distribution has been shown on the slide. Next we will see Rayleigh distribution. Rayleigh distribution finds application in describing envelope of noise passed through a bandpass filter. It also finds application in describing multipath propagation where no line of sight is present. The distribution and density function are as follows: capital Fx of x is equal to 1 minus exponential of minus of x minus a the whole square divided by b for x greater than or equal to small a, and 0 elsewhere. Small Fx of x is equal to 2 by b x minus a into exponential of minus of x minus a the whole square divided by b for x greater than or equal to a and 0 elsewhere. The graphs corresponding to the PDF and CDF of a Rayleigh distribution have been shown on the slides.